so sweet. I'm going to try this, and let's go ahead and rock. Let's do the chalk talk right now. We got kind of how I set it up. So let's just go ahead and get it out there, and so we can kind of always refer back to it. I want to take us through this chalk talk, which is talking about the ANOVA, giving us an example. I'd like to also then talk about the assumptions of the ANOVA and when it's robust, just like we did with the two-sample test. Then do a few examples, have a breakout, and then look at a few more examples, and then we'll finish up. So we obviously have a lot to do, so we'll go ahead and get started. So I will come out this way. If you want, this will be super helpful while I'm writing this up here. If you can find a pen and a sheet of paper, you don't have to do that, obviously. But if you can find a pen and a sheet of paper, I think this would be very helpful in the future to really, I basically get down everything I'm about to put down on the board. This will really help you own what an ANOVA table actually is. So where is, I'm going to use some white chalk here for some of it and some other chalk for some other stuff. So let's say that I have a group. Let's say I have group 1, group 2, and group 3. All right, and in those groups I have the observations 3, 5, and 7, and I have the observations 10, 12, and 14, and I'll have the observations 20, 22, and 24. And keeping in mind, we're thinking that group 1 has its own distribution, group 2 has its own distribution, and group 3 has its own distribution, and we're saying that they're all, our assumption is, and it can be robust to this assumption, but the actual assumption behind the math is that they're all normally distributed with some mean. And of course, we're assuming that the standard deviations are all equal. And we'll talk about if it's robust to that or not. But we're assuming, I'll just label them all as sigma. We're assuming that there's 3 distributions and that they have 3 means that may be equal or may not be equal, or different pairs of them may not be equal. But, and this is what we get. We only get a look. We get a little bitty window. We get 3 observations from group 1. We get a little look at 3 observations from group 2. We get a little look at that. And just by judging at that, would you think, just intuitively, no mathematics here, would you think that the evidence would suggest that mu1 is different than mu2 is different than mu3, or do you think that the evidence would suggest that it's possible they're all equal, but does the evidence suggest they're different or that they're the same?
Different.
And I can see it's going any number of ways, but I think that, yeah, these are 3, 4, 5, that's 10, 12, 14. That could happen at random, but if all of these were equal, if all of those mu's were equal, the probabilities that you would observe something as extreme or more extreme than really 5 is the mean here would be, and 12 here and 22 here, that they wouldn't be mixed up, that you'd actually have the 3 lowest here, the 3 middle ones here, and the 3 highest ones here, would be very small. This is certainly evidence against the null hypothesis, and I'll put the null here, against the null hypothesis that mu1 equals mu2 equals mu3 versus the alternative that at least one pair are different. Notice I have to write it like that at least one pair are different. That's an L, believe it or not. So that's our null and alternative hypothesis. So how are we going to do that mathematically? We certainly think that is intuitively. So I'm going to eventually build an ANOVA table, but for now I'm going to do it graphically. Let's just say I have my scatter plot here, and that is mu1, or not, sorry, this is group. So this is G-R-O-U-P. That's group 1, 2, and 3. Back that up just a little bit. And I plot them. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I hate when I do that. I ran into that. So that's 3, 4, 5. So that's 3, 5, 3, 5, 7. That's 3, 5, 7. Doesn't have to be exact here for our purposes. 10, 12, and 14. When did the overriding 10, 11? So that's about 10, 12, and 14. And this one up here is about 20, 22, and 24. So that would be about 20, 22, and 24. Great. So those are our plots. Certainly it looks like this is evidence that group 1 and group 2 and group 3 all have different means. I would say that that is, if they all had the same mean, you would expect something like this. Group 1, 2, 3, you'd expect something like this. Right? If they were from the same, you'd expect a cloud of points where some were bigger than the other ones. You wouldn't expect group 1s to all be lower than groups 2 and group 2s to all be lower than group 3. That wouldn't happen. That'd have a very small p-value. So, okay, but still, that's just subjective based on what we're looking at. Is that how we're supposed to solve these problems, is just looking at it? And no, what we're going to do is analyze the variance. But as is common, it sounds like ANOVA, analysis of variance. It sounds like we're testing variances, but we're actually using variances to test means. The ANOVA is a test of means. So that's the first misnomer. So we're analyzing the variance to test means. How are we going to do that? This is how we're going to do it. So if you have that down right there, what we're going to do is create an ANOVA table. And here comes the, no, actually, you know what? Shoot. All right, just make it. I know everybody's going to start writing it. We're going to take a, let's see here, make that have 1, I always mess this up, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We'll leave it like that for now. Actually, you can put this a T, an E, and an M. And that is our ANOVA table. Great. So this is how we're going to answer that question. But first, what we're going to do is just kind of talk about it and make sense intuitively. All right. So what I'm going to do is compare two models. And I'm going to count essentially the residuals here. So what we're going to do is say, hey, one model, if these are all equal, let me just ask you a question. If mu1, mu2, and mu3 are the same, then what is my best estimate right now of that same mean, of that mutual mean? Given the data that I have here, what would I do to get my best estimate of the mutual mean there if mu1, mu2, and mu3 really are the same?
Sum up all of them and divide them.
That's our best estimate.
Can't hear you. Can't hear you. I hear lost. Voice is lost. Hello.
Can anybody hear?
Yeah, I think we can all hear each other, but we can't hear him.
I cannot hear him. No, I cannot hear Bivin. Yeah.
Can't hear you.
Can't hear you. Still can't hear you. Oh, you. Bivin, we can't hear you. We cannot hear you.
I guess he cannot see us.
No audio.
There he goes. Did you see his face? He's like, oh. Was everybody doing this? Next time we got to do this, right? When he does the pow like this at the end, we got to go like this when we can't hear him. Ashwin, you're still at work, my man.
Yeah, I know. So stuck here. And I came in at 7 o'clock this morning.
Yeah.
What do you do?
I do data analytics, but this is one of those days where, just had to finish up stuff.
His phone died. Okay. They said his phone died.
Yeah.
That is unfortunate.
Hey, Max, I always wanted to ask you this question. So what are all those books behind you?
Those are books that I've read when I was doing my PhD, or at least a fraction of them.
Wow.
Wait, what did you get your PhD in?
My PhD is in philosophy. I have a master's in theology and a master's in philosophy. This is my third master's.
Man.
I'm going to do a
Wow.
second PhD after this.
That is impressive.
My PhD stands for phenomenally dumb. You want someone real smart? It's my son, Joshua. He's in the class. That good-looking young man right there.
Oh, really?
I have a feeling your opinion made me buy it.
We're gonna have to. We can't figure out whether it's biased or not because we can't compare because we don't have our ANOVA chart yet. Okay, one.
All right.
Count all three. All right, we'll translate here.
Is this how we're going to study today?
He's going to figure out that's going to be the grand mean, I think.
No, if the grand mean 13 is a good model, if the separate means are better.
Let's right. Equal means model. All right. So have you guys anybody, is 13 the grand mean? Yes, it is. Now he's going to see the distance between each one of those and the grand mean. Josh, the black and white filter. Okay, those are the residuals. So the residuals are the difference between the observation and the grand mean. Okay, 3 minus 13, 5 minus 13, 7 minus 13.
Are we still in the scenario where we don't have audio?
Yes, we are. That's why. I think his battery died out.
Okay.
We should have messed with you. We should not responded. And you would have got freaked. Got like 10 minus.
No, not to understand what he's saying.
Yeah, so he's saying take every observation and subtract it from the grand mean to get the residual. 14 minus 13 is going to give you 1. And do it for the group 3. I'm translating here. I should just make up some crap as we're talking, just to laugh.
Please don't make up crap.
Okay, so he squared them. What are you doing? So now he's going 3 minus.
He's taking the square of it.
Yeah, he's taking the square of it.
Yep.
So 7 minus 13 is minus 6 squared is 36. So that's the square of the means. So take every observation, subtract it from the grand mean, get the grand mean first, and then square it. Yep. Doing well. Excellent. It's big relative to what? Okay.
Try to beat me if you can.
I feel like last week was the only week without technical difficulties.
Orange. See, okay, the orange chalk here. Now we're going to take the means and we're going to subtract them from the means and square those, as opposed to from the grand mean.
Yeah, I think he's looking at the individual group means and then subtract
Yep.
each operation from it.
That's right. That's right. So he's going to the mean of each. So he's going to do the same thing. Instead of using the grand mean, he's going to do the same thing using the mean for each group.
He's comparing the group means to the grand mean.
Yep.
So in just a quick question. So in this scenario, is the group mean going to be the square root of 462?
No, he took the average of the individual groups.
No, that's understood. But he's comparing the average of the groups to what?
To the grand mean. He's comparing those orange ticks are the group means. He's comparing those to the 13 that he drew all the way across.
Gotcha.
Now he's getting the variance of separated means. Zero squared. 7 minus 5 is 2, and squared, that's 4. So basically the same thing. Yep. G1, G2, G3, 4, 0, 4, 4, 0, 4, 4, 0, 4. And then the sum of all that is 24. Yeah, it's huge, big difference between them. You'd expect them to be the same if they were equal. For audio that fast. Yeah, but so we got to divide those suckers by the degrees of freedom. This is a class where we could use audio.
I think his phone is up now. Might be.
Any questions?
No.
Oh,
You're back.
Oh, you charging your phone? You were charging your phone.
Yeah, it takes a little while to charge. I'm sorry. For whatever reason, I didn't keep track of it, and it blew out. But maybe you want me to turn it back off. I don't know. So we can catch back up here. But
Professor Sedler.
Oh, yeah, go ahead.
Yeah, could you please summarize it again if you don't mind?
What's that? I'm sorry?
Could you please summarize the whole thing again if you don't mind?
Yeah. So all of that right there is we're saying this. We're saying, hey, we want to know, we got two models. right? We got two models that we want to compare. One is the equal means model. That, of course, is the model if we assume the null hypothesis. If we all assume they're all equal, then the equal means model, that would be the best guess of that equal mean. So we want to see how well the data fit that particular hypothesis, fit that scenario, fit that model. So that's it. The green one you're looking at here is the equal means model. How are we going to mathematically assess that? What's the most intuitive measure of how well that model fits? To me, that would be just look at the distance each point is from that estimate. Is 13 a good estimate of this data? Well, let's see. Let's look how far that is from it. The problem is this. What we're always going to do is our residual, even when we hit regression, our residual is equal to the observed minus the expected. And you can commit that to long-term memory. Your residual is an observed value minus the expected value. So under the model is what gives us what we expect the value to be. That's the model. Those 9 observations up here, these are the observations. So observed minus expected is going to be 3 minus 13. That was the negative 10 I put over here. But notice that it got squared to be 100. I'll tell you why here in a second. So notice that this was negative 10. This one is 5 minus 13. That's from here to there. That's negative 8. And this was 7 minus 13. That's negative 6. Those are all negative numbers. Of course, these will all be positive numbers because that's going to be 24 minus 13. That's 11. That's going to be 22 minus 13. I mean, that's, what is that? Yeah, sure, 11. This one is 9, and that one is 7. The thing is if you add up all of the residuals, you'll be adding negative numbers and positive numbers, and mathematically they will always equal 0. If I summed all the R's, that will equal 0 every time in regression, ANOVA, whatever. So that doesn't help. That implies that there was no error. Regression is a measure of error, the distance between the model and the observation. So that's no good for us. So for one reason, we want to square them so that they all become positive so that we can really get a measure of how well this model fit our data. Cool. And I'll tell you another reason why we like to square them here in a second. But for right now, just think of it that we're squaring them so that they're always positive, and so that the bigger this number is, the worse the model fit the actual data. So we're comparing it. That was for the equal means model. That green stuff's for the equal means model. The whatever the color of this is, orange, is for the separate means model, which is what we're fitting in the ANOVA model. And in ANOVA, we're comparing the equal means model to the separate means model. The separate meaning we're going to let each group have its own mean, because that's the worst case scenario for the alternative. At least one pair are different. Well, what we're going to do is let all of them be different and see if that model fits significantly better. It will always fit a little bit better. If it fits significantly better than the equal means model. And if it does, then that'll be evidence against the equal means model. So let's ask any questions you got on that, because that's the big strategy. We're going to fit the equal means model and the separate means model. If we can explain significantly more variance, this is all variance, right? Variance is, when you think about the definition of variance, right? Variance is this. This is the variance, right? When you look at the equation of variance, it's the sum of xi minus x bar squared divided by whatever, divided by n or n minus 1, depending if you want an unbiased or biased estimate. But for now, I'm just focusing on this part. And it's simply an observation minus its mean, minus the expected value. That's what we're doing right here. That's why this whole thing is called analysis of variance, because this guy over there is the sum of Ri minus x bar. It's the sum of, it's just the sum of Ri's, which is xi minus x bar. This guy right here is that value right there. That's why this is called the analysis of variance. So let's get back to the big picture. The big picture is the sum of squared residuals of the green one are 462. If I let all of that charade on the orange one was letting them have their separate means, so that the average of these guys is 5, the average of these guys is 12, the average of these guys is 22. So that's me putting the dash across these. Look how much smaller those residuals are. And those, if I add up those residuals, I get 4, 4, and 0 because 5 is a great estimate of 5. And 12 is a great estimate of 12. And 22 is a great estimate of 22. Those landed straight on. So that's 404. Basically 4 times 6 was 24. So by allowing the separate means, we ended up explaining from 462 all the way down to 24. So we had a significant reduction in the error. Essentially, that's a measure of error is the residual. Anybody have any questions on that piece, though? Please, if you have one, I guarantee you somebody else has the same or a different or a different question.
Yeah, I have a question.
Yeah.
So, in the assumptions, we have like the standard deviation is equal, and then we are testing the variance. So, like it's like we are again, because variance is nothing but square of standard deviation of the deviation. So, how come it's like we are again testing the assumption what we have made?
I see what you're saying. It's saying if the standard deviations are assumed to be equal, and we're doing a variance, and the standard deviation is what the square root of the variance, are we really testing the assumption of the model as we're going in by doing this exercise?
Yep.
Okay, so I see what you're saying. And when we hit the ANOVA, you're going to see. I think you're going to get a better answer to this question. But first thing to remember is that we're using the variance to test these means. And the way we're doing it is we're saying, hey, let's let these separate means describe different estimates of these 3 groups, and then let's look at the average deviation away from it. So what needs to happen in order for this argument here to have any validity, we have to make sure that what we're assuming here is that group 1, group 2, and group 3 have the same standard deviation. Because if they don't, let me show you an example of a picture superimposed in here of what would happen if they don't. If they don't, you're not playing on an equal playing field. So let me do the same one. Let's say that this is 1, 2, 3, and let's say that this is 1, 2, 3, and let's say that this one is 1, 2, 3. And so if that's the case, this one clearly looks like it has bigger standard deviation than this one, and this one looks like it has bigger variance or standard deviation than this one. And when you start summing up for the equal means model, or even for the separate means model, or even for the equal means model, this one is going to the group 3 is going to have more influence than group 1 or group 2 because its residuals are bigger. You've got to make sure.
So I think, is it fair to say that by assuming that the standard deviations are the same, if we observe any differences between the groups, that has to be because of the means, not because of the variances? Is that why we are assuming?
Sure. Essentially, yeah. That's another way of saying. I guess what I'm trying to say here is that when we start summing up these residuals are going to totally swamp out those residuals there, even though maybe relatively speaking, these are much farther away. So this group 1 is going to have hardly anything to do, even though they're so close. Group 1 is going to have hardly any say in what's going on in the sum of squared residuals because it doesn't have a possibility of even competing with this guy. Because these residuals, think about what a residual is. When you square 2, you get 4. But when you square 3, you get 9. So 2 to 4 is only 2, but 3 to 9 is 6. When you square something, the bigger the number, the more it can swamp the sum. So when I square 2, it's 4. When I square 3, it's 9. When I square 4, it's 16. 4 to 16 is 12. Right? When I square 5, it's 25. Now I'm up to 20. So when I square this guy here, it's going to totally swamp out the difference of what we're doing, of what we would have here. Another explanation of why we have the equal standard deviation assumption, this is essentially why right here. But another reason why we have that equal standard deviation assumption is when we run our tests, what we're going to do when we run our tests is we're going to pool the standard deviation, just like we did in the pooled sample t-test. And when you pool the standard deviation, I'm going to get a sample of S1, an S2, and an S3. And the pooled standard deviation, right, the pooled standard deviation is thus N1 minus 1 times S1 squared plus N2 minus 1 S2 squared plus N3 minus N1 S3 squared divided by N minus 3. And I'll just call that the pooled variance. So if that's what you're going to do, if you're going to use all of these to estimate, because we're going to end up, somebody asked this in the quizzes, how is this very useful if I'm trying to test, say, 10 different means and I reject, if the alternative is at least one pair are different, well, which pair is it? Is it 1 in 10? Is it 2 in 10? Is it all the pairs? Is it half the pairs? There's too many combinations there. What does it really tell me? What we're going to do in Chapter 6 is actually run those tests. We can get SAS to run all of those tests very quickly, but in order to run a test, you have to divide by the standard error, and the standard error is this estimate. And if you're going to use one estimate, and that's going to increase our power because we're going to have more observations estimating the standard error. But that's only powerful. You can only have all these observations estimating the same standard error if they're all estimating the same thing. Right? This can't be sigma 1, sigma 2, and sigma 3 and have sigma 1 smaller than sigma 2 and sigma 3 and do this, because S1 is estimating something different than S2, and S2 is estimating something different than S3. It makes no sense to pool them together. So the best answer I have at the moment, because it's a super important question I want everybody to remember, the question being, I think, is why is isn't this a test of standard deviation? Or what I'd really like to steer the question to is, why is the equal standard deviation assumption exist? Why is that important? And those questions will be answered in the future, but for right now, if they were different, then group 3 would swamp out the effects of group 1. We need to keep them on equal playing fields. But number 2, more importantly, it's going to allow us to use all 9 of these observations to estimate the standard error, because our assumption is that all 9 of them are estimating the same standard deviation. And if that was not true, I would have to use these to estimate one, and have to use these to estimate another one, and I have to use these to estimate another one, and I wouldn't be able to pool the standard deviation. And the last piece is the number of observations that you're using, of independent observations, that you're using to estimate this is what's increasing your power. Of course, the more, we've already established that, the more observations we have, the more power we have. Right? The more power we have to detect significant effect sizes and significant differences between these means. So, so the answer to your question is going to continually become clear while we go through this. But at the moment, I guess I'll have to table it there, because at the moment I just want us to see exactly what the strategy of this test is and how we're counting sum of squared residuals to get there.
Is it the case that, or is it not the case that the sum of the square, between the observed and the expected value for within the groups, or I think you have them as separated, will be smaller than those between the groups, which I think you have as equal, because it's always the case that when you're comparing to yourself, there's going to be, it seems to be the case that there will be less residuals within the group than it is between, because 13 is just a number, and then every other residual that you're comparing to that 13. In other words, your 462, it will always be greater than your 24.
That is true. Your sum of squared residuals from the equal means model will always, mathematically they could be equal, but that's only if you have this situation. They're only equal if your observations
if they're all across. Yep.
That's right. And that's usually, of course, not the case in practicality. So just in random chance, this number, whenever you allow the flexibility to have three separate means, whenever you have the flexibility to have different means, of course you're going to custom make that mean, you're going to have smaller residuals. The question is if you have significantly smaller, and we haven't gotten to where we're creating that p-value, but that's the crucial question. Clearly here it looks like, of course, 462 is smaller than 24, but what if it was 462 versus 400? Is that evidence or is it not evidence? And so that's what we want to get to when we create this p-value, which is actually which is actually also going to answer the question of this equal standard deviation. And I think you'll start to see why that assumption is important and see the big picture here. But let me give you one more idea, is what if you had something like this, 1, 2, 3, right? And let's say that the null is true. If the null is true, we would have something that looked like this. You know, just by random chance, we might have some things that look like that. They're not all going to be, you know, you might even have, depending on the standard deviation, you might have these kind of closer together and these far apart, but because you're only taking 9 observations. It's just a toy example. But the point here being that look at what happens when I take the grand mean. I'm just eyeing it here. The grand mean looks to be about there. And the separate means look to be about, the way I've drawn it, kind of right about there. And so what was just said was, of course, the distance between each observation and the green line squared is bigger than the sum of the distances between each observation and the orange line squared, but certainly by not as much as 462 to 24. And one more piece is this. He talked about the within sum of squares and the between sum of squares. The within sum of squares is the 462. The within sum of squares is the distance. I'm sorry, the within sum of squares here is actually 24. The within sum of squares is the between this and the separate means model. Between this and the separate means model. Whereas the between sum of squares is the difference, the sum of squares between the orange line, the separate means model, and the equal means model. That's how much is being explained. So notice here in this observation, the difference between the mean, we know that the difference between these guys, when the evidence is against the null, we know that the orange sum of squares squared, the orange residual squared, is 24, right? And we know that the distance, look at the distance between the equal means model and the orange thing. That purple line is the distance, that's a residual, between the the separate means model and the equal means model. That one's kind of small, but this one's big and this one's big. So in this case, your within sum of squares is very small, and your between sum of squares is very big. And I'm going to show you the lines in the ANOVA table of the within and the between. But in that case, you're going to have evidence against the null, evidence for separate means. Here, we've got, again, the within sum of squares is the distance from here to that orange line squared, from here squared to this distance from here to here squared, and from here to here squared, but here. So the within sum of squares will be from the white to the orange. The between sum of squares will be from the orange to the green. And so when you have evidence against the alternative, when you have evidence, essentially not enough evidence against the null, that means that the separate means model, most of them probably aren't very far away from the equal means model. And the between sum of squares will be small, but the within sum of squares will be bigger. And that's what we want to measure, is that ratio with the ANOVA table. And so
were you just comparing the means of each group to the grand mean?
The means of each group to the grand mean. That's right. That's the between sum of squares.
And what was the so the between sum of squares is the comparison between the mean and the grand mean, and you're accounting for what at that point? That area? I'm trying to figure out what, because there's a certain variability that's being accounted for, and I don't know whether it's the between sum. The difference between the orange and the green line.
The amount that you're explaining is the between sum of squares. The amount and the variation, that's what analysis of variance really is you can measure the variance of the observations from the equal means model. So I've drawn my equal means model up there. So there's my green's my equal means model, and I can take, that's just x bar. So the variance of these points is a function of the sum of the squared residuals, the distances from white to green, from this to green, from this to green, that 462. Now, how much of that am I explaining with my separate means model? How much you're explaining of that is exactly the distance from here to here squared, from here to here squared, and from here to here squared. And how much you're not explaining is what's left over, the distance from the white to the orange, the within sum of squares, the white to the orange, the white to the orange, the white to the orange, that's how much is left over. And if what you're explaining, this is really the whole big deal, if the amount that you're explaining of that 462 is significantly greater than the amount that you're leaving, right? If I make that a ratio, if I say, well, how much of this, let's say I'm explaining 400, I'm about to break it down. Well, let's say I'm explaining 400 of this, and I'm leaving 62. Well, actually, you've got it right here. This is what it's going to be. I'm leaving 24, and I had 462 total. So 24 is the sum of squared residuals from the white to the orange. That means from the, I mean, we could do this right now. Let's just do it in our heads, right? Let's do that. So what I'm saying is that 462 is the total, and we're going to make it an ANOVA table here real quick. 462 is the total. This is the within. This 24 is how much is left after the separate means model got its hands on it. So that must mean that 462 minus 24 is explained by the model. So what is that? 438. So 438 should be how much is explained by the model. So let's look at it. So from, what is this, 5 to 13. Let's do that. I'm just doing 5 from here to here. 5 to 13 is 8.
8. Are you going to square that now?
8. So I'm going to square that.
So that's 64.
Good. So 12 to 13 is 1.
1 squared, 1.
So that's 1. And 22 to 13.
9 squared is 81.
So 20 squared is 81. Where am I breaking down here? 462. So that's not quite 438. Hold on a second. I'm going to have to break my ANOVA table out here. So within and the between 5 to 13 is 8. I'm making one little mistake. 12, 13, 22 to 13. So clearly that doesn't add up. Give me 1 second to think about where I'm making a mistake here. We'll figure this out. It's 464, 24. So we're saying that is 438. So that should be the sum of squared between. So here, the sum of squared between is equal to the sum of the xi bar minus x bar squared. In this case, from I equals 1 to 3. And the sum of squares within is equal to the sum of the I equals 1 to, in this case, 3. So the sum of squares within is y equals 1 to 3, and then the sum of j equals 1 to 3 of xij minus xi bar squared. And so that's xi bar is 5 minus 13 is 8.
That should add up. 462. I'll find my mistake here in a second, but in the interest of time, let me go on with the ANOVA. I get what you're saying. I'm going to find it when we hit this ANOVA. But yeah, the total sum of squares is the within sum of squares plus the between sum of squares. The between sum of squares is the mean. It's subtracted out, right? Yeah. What you have calculated on the left is the total sum of squares, the 462, and then you're subtracting up to 24, and the remainder is the, let me see where it is here. Yeah, that's how much you explained. Yep. That's how much is explained. If you divide that by that, you get R squared. Yeah, well, so yeah, you got me on that one. I will find it here in a second. It'll be an easy mistake. But I want to make sure that we get to the ANOVA so everybody sees where these values are coming from. And we'll find it. I'll leave all this up here. My apologies, I don't have it right off the bat, but this should just not account. Isn't it the total? Isn't it the case that the all the way on the left you have the total, and then what you've done is you subtract and then the 24 is a within, and the between group is derived from taking the total from the within? The between is derived from taking the total, which is the 424 minus 24, which is the within the group. So the between the group is the difference is 424 minus 24. 462. I'm looking at mine. Yeah, 462 minus 24. Minus 24 gives you the between group. That's right, and that's 438. The problem that I'm having is that the between group should be the sum of squares between the separate means and the equal means. And that from 5 to 13 is 8, and 8 squared is obviously 62. And this from 12 to 13 is 1, and from 22 to 13 is 9. And 64 plus 1 plus a, yeah, it's 146 or thereabouts. 146. So that part's breaking down for a second. I apologize. I'm making an easy mistake somewhere. But, well, I know. The good thing about it is it's all math, so it'll all work out here in a second, or it'll work out eventually. But let me get to how you're really going to read it and apply it, and I'll make this all fit together later. So and later being soon tonight. The big picture is this. How are we using a variance to assess this idea of equal means? And the way we're doing is, well, let's assume that the equal means model is appropriate. If it is, then x bar equals 13 should be a good estimate of all the points. And we're saying, well, let's measure it. How can we use a measuring stick? Well, let's see on average, or let's see how far each point is from that model and square it so that they're all positive. And that turned out to be 462. And then we said, well, now let's assume that this model, let's let them compete. Okay, well, let's assume they're all different. And if they're all different, then let's let them all, the best estimate of them being different is to let them have separate means. We give them a separate means model. We add up the same residuals, the residuals squared, and now they're only 24. And then we said, well, okay, well, great. It's easy to see that 462 is different than 24, but let's put it in this, that's what the ANOVA table is doing every time. And let's go ahead and put this into the ANOVA table, and we'll answer some questions here, and I think we might all come out on top. So this is your ANOVA table.
I think if we multiply 146 with 3, that is equating with 462 minus 24.
That's it. It's the sum of squares between is 3 times that. Yeah, the sum of squares between is equal to 3 times, or in times, the xi bar, where I is your group, minus x bar, which is, that's the total one, squared. And that is because that total one, that is an estimate of, why is that? Well, that's a good find. Let me keep going with this, but I'm glad that worked out. It's n times, n is the number of groups, n times this distance, the sum of this distance squared. But long story short here, let me grab this. This is, okay, so the degrees of freedom. The degrees of freedom are the number of your total sample size minus the number of parameters you had to estimate to get that model. The number of parameters you had to estimate to get that model. So under the equal means model, this model here, how many mu's did I had to estimate? If I assume they're all the same, then there's only one mu, and I only estimate that with one x bar, or in this case I call it x bar for global mean. So I'm only estimating it once. I only had to estimate one parameter with the equal means model. That's going to be important for the next couple of weeks. One parameter with the equal means model, that makes this 8. That makes that 8 right there. We had 9, sample size is 9, that's 8. The error one, so this is the equal means model. I'll call it EMM. That's our equal means model. This guy here, this is our full model. I'll call him the separate means model, but this is the reduced model and this is the full model. So this is the full model, also known as the within. You can call this the full model or the separate means model. Let me put that back in here. This is full, separate, within. This row right here could be called the full model, the separate means model in this case, or the within sum of squares. And this last one up here is the between. It's not labeled as a model because this row is how much you explain. That's the between sum of squares. This is how much is left. Let's go ahead and fill them in. For the separate means model, we need to estimate 3 means. We had 3 parameters. For the separate means model, we had 3. That's just your number of groups. 9 minus 3 is 6. So all of this is n minus number of parameters. Equal means model is 1, so it's 9 minus 1 is 6. 9 minus 3 parameters for the separate means model is 6. 8 minus 6 gives me 2. All I have to do is subtract up to get that one. And that 2 can be interpreted as the advantage that your full model has over your equal means model. What kind of advantage does my full model have over my equal means model? It has 2 more parameters to explain variance with. So this will always be the difference in those 2. So then I look at the sum of squares. This guy here is 462. And what else am I looking at? I'm looking at this guy here, which is 24. My difference, we already said, was 438. And by now, that's probably pretty apparent that those are just the sum of squared residuals. This is known as the sum of squared residuals, and that's known as the sum of squares between. That's the sum of squares within, and this is the sum of squares total. So then what I need is to say, hey, I took 2 more parameters to explain this much variance. 2 more parameters to explain this much variance, so I divide that. 238. How much more am I explaining per degree of freedom? That's 438. That's 219. This here, 24 divided by 6. That gives me 4. And that's exactly what we were talking about before. When your between sum of squares is much greater than your within sum of squares, and of course it's a function of your degrees of freedom too also, if you didn't take very many more parameters to explain that much more, then your ratio of the mean squares, the mean being the sum of squares divided by the degrees of freedom, the ratio of this mean squares will be big. If you don't explain much like in this scenario, if your within is much bigger than your between, then this between will be small and the within will be big. And what I'm saying is this F statistic here is simply the division of 219 divided by 4. I forget exactly what that is. So 219 divided by 4 is 54.75. So that is 54.75. And then long story short, after that is another reason why we square them. because we could have just taken the absolute value over here, right? In order to make these things positive, we could have just taken the absolute value. That would have made them all positive. We could do it. The reason why we square it is because it turns out we can show mathematically that this division, that the division of the mean squared between with the mean squared within follows a particular distribution. If I was to repeat these samples over and over and over again, I would get a bunch of different F statistics. And what this is an F distribution with 2 and 6 degrees of freedom. That's what an F distribution is. We've already talked about T distributions a whole bunch, right? And the bigger the degrees of freedom of the T distribution, the closer it approximates the normal distribution. The closer it approximates the normal distribution. Distribution is the same. It has 2 degrees of freedom, and the bigger those get, actually, the more it approaches the normal distribution. But with an F26, that's a particular shape. Once I have the shape, I plot 54.75, and that becomes my p-value. And this p-value here will be very, very small. And that's the p-value that SAS is giving you. And so the conclusion here is, so what happens here? All we did is we looked at the sum of squared residuals. We took the mean squares. From the mean squares, we divide them, and we get an F statistic. If that F statistic is huge, it'll give us a small p-value, saying the probability of observing a ratio this big under the null hypothesis that there is no difference in means. This would happen very rarely under that assumption. And if that's the case, we're going to reject that assumption. And our only conclusion we can make from this is that there's enough evidence, there's an overwhelming amount of evidence in this case, that at least one pair are different. That's where we have to leave it here, that at least one pair are different, right? That at least one pair are different. It could be 1 and 2, 1 and 3, 2 and 3, or 1 and 3. Clearly, we can see that if there's any one that are different, 1 and 3 should be significantly different. But we don't know yet if 2 and 3 was enough, or this one and this one was enough. We're going to have to leave that for Chapter 6, where we're actually going to do individual for every pairwise individual t-test, those confidence intervals and hypothesis tests. But it's not. It sounds tough to do calculation-wise, but that's the easy part. We let SAS do that. We're going to have to make another adjustment called a multiple comparison adjustment, and we'll approach that in Chapter 6. But that's the big picture. We're going to first do an ANOVA. If we reject, then we've got more work to do. We've got to go look under the hood and look at all the pairwise comparisons. In the quiz, though, somebody said, hey, what if I had 10 means? Isn't the ANOVA pretty worthless? I'm paraphrasing. They didn't say worthless, and I might be missing a little bit. But the big gist of it was, at least I want to approach, is if there's 10 of them and I reject, that doesn't tell me very much. That just tells me at least one pair in these 10 choose 2 pairings is significantly different. Great. What does that tell me? Well, it could tell you a lot if you failed to reject. If you failed to reject, that would be there's not a significant difference, and the conclusion is there's not enough evidence to suggest any of the means are different. And that's not that means that you can't go in there and do more research, but the ANOVA can be very powerful to tell you don't look in these 10 means. These 10 means are not significantly different according to our p-value. And then you can go look at a different 10. So that could save you a lot of time. But okay, so we've gone really in depth on a bunch of this, and this was really good to remember that piece, that it's 3 times the sum to get the between. But that's where this number comes from. We know where that number comes from, and we should know briefly how to get this whole ANOVA table. Now, that would be a shame if we had to do this every single time. We had to write all this up. Wouldn't it be nice if we had a computer program that would just generate this table, and we could get our p-value? And that's what I want to show you here real quick. So if I take this out.
Can I ask you real quick, I'm sorry if I missed this, but what's the M, E, and T in the first column?
Sorry, this is model. This is what you'll see in SAS. This is model, this is error. That's a great question. This is model, error, and this is total.
Okay. Thank you.
All right, yeah. So that's great. I just breezed right past that. And that is going to be huge